Hi everyone, thank you for joining today for What You Need to Know Disinfection By Products webinar with our speaker, Darin Skutt. I'm the moderator for today, Ashley Swingle. A few housekeeping items before we get started. We are recording this webinar and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we'll receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or the recording of the presentation, please contact us. We encourage you to share the recording within your network. Listed here is our website that you can visit to register for upcoming webinars. At this time, I would like to take the opportunity to introduce our speaker, Darin Skutt. Darin has worked for Carus for over 22 years, with the last year in the Technical Solutions Group. Darin conducts laboratory testing and product demonstrations for Carus's municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentations, and the installation of safe chemical handling and dosing systems. He is a graduate from Illinois Wesleyan University, Bloomington, Illinois, with a Bachelor of Science degree in Chemistry, ACS certified. Mr. Skutt is a member of AWWA, WEF, and the American Chemical Society.
Thank you, Ashley. So outline of our presentation today, we'll talk about the different options for permanganate products to be used for disinfection byproduct control. We'll then specifically talk about the two stages of the disinfection byproduct rule. We'll go through how you determine how much permanganate you're going to feed when you have an issue. So we'll go through jar testing, and then we'll go through multiple case studies. If you have any questions, please feel free to type them into the question pane, and we'll get to them at the end of the presentation. So many of you will be familiar with the products that we sell at Carus. Our main product line is Carus potassium permanganate. It's the purple sand that you see there in the picture, and its chemical formula is KMNO4. One thing to keep in mind is when you're buying Carus potassium permanganate, it's always going to be found in the crystal form, so that purple sand that you see. Typically, you'll buy the dry product in multiple container sizes, and then you'll make it up into solution prior to feeding it. The product's shelf life is very stable. So Carus that you buy today, as long as it's in the sealed container, will be good today, 2 years from now, 5 years from now. It's going to stay the same percent active. It does not lose strength over time. Now, one thing to keep in mind with permanganate is in the case of Carus potassium permanganate, is it is hygroscopic. It does pick up moisture from the outside atmosphere. So if you do open a container of the product and don't seal it, if you're in an area where there's a lot of high humidity, the moisture will actually attach to the permanganate itself, and it will start to lump up. Now, we do sell a free-flowing grade of permanganate that has a free-flow additive that helps prevent some of that, but it can't prevent all of it. So especially in June, July, August, September, when we have a lot of high humidity down south and in the Midwest, you'll definitely want to make sure that you seal the container back up if you're not going to use it all at that time, so you can prevent that lumping. Like I said, one of the things that you're going to do when you have Carus is you're going to have to make it up into solution. There's a very low solubility of potassium permanganate in water at room temperature. So the max solution that you can make is a 5% solution. So what we typically do is we recommend that customers make a 3% solution. 3% is easy to remember because it's a 1/4 pound of dry permanganate per gallon of water. You'll need about 10 to 15 minutes of mixing to get that permanganate into solution, and then you'll have a 3% solution that you can then dose to your application point. The Carus product is available in 55-pound pails, 330-pound drums, 3,300-pound cycle bins, which are returnable containers, recyclable, and then we also supply it in bulk. Like I mentioned, we do have a free flow grade that has the free flow additive, so that product can then be fed and prevent some of the lumping issues that you might have. There's also a technical grade that has less of the free flow additive, but we recommend that if you're going to use the container all at once and not through a continuous feed system. If you are looking for a Carus potassium permanganate system, we do have an equipment partner in UGSI that you can find online, or you can call us and we'll direct you to them, where you can purchase feed equipment for the dry permanganate as well. Now, the other product we're going to talk about is Carus liquid permanganate. So this is sodium based. It's the dark purple liquid that you see in the container with the white cap. So it almost looks black when you see it in the container itself. As you dilute it down, it takes on the same distinct purple color that Carus potassium permanganate does in solution. The chemical formula for Carus liquid permanganate is NaMnO4. You're only going to see Carus in the liquid form. It is sold in both a 20% and a 40% concentration. And the shelf life for this product is also stable and will keep indefinitely. So we have products that take one bulk load a year and it stays at the same 20 or 40% concentration during the course of that full year. It does not lose strength. Something like hypochlorite fluid or hydrogen peroxide will lose strength over time. The Carus product does not. We have product that we have stored on site for 1, 2, 3 years, and it does not lose strength over that time. So you can take one shipment in and then use it over the course of a year or 2 years, and you won't lose any solution strength. Now, the reason we sell the Carus sodium permanganate is because that change from potassium permanganate to sodium permanganate changes the solubility in water of permanganate immensely, which allows us to have a 20% and a 40% concentration of the sodium permanganate, so we can sell it as that concentrated liquid. Like I mentioned earlier, the potassium permanganate has a max solubility of 5%, which means you'd be shipping 95% water, which isn't economical, which is why most people choose to move to sodium permanganate if they're going to feed a liquid to their application. The Carus sodium permanganate is available in 55-gallon drums, 250-gallon IBCs, and we provide a lot of it in bulk to many water plants across the US, which is typically about a 4,000-gallon shipment. Now, one thing that we get asked a lot about permanganate is, does it matter if you're using potassium permanganate or sodium permanganate? Well, all the reactions are the same. It's the permanganate that's actually doing the oxidation. The potassium and the sodium only affect the concentration that you can have in solution. The other thing we get asked sometimes is there a difference in coloration? Well, it does not matter if it's potassium or sodium permanganate. In water, before it reacts, it's going to have that distinctive light pink to dark purple coloration. So what you can see here on this slide is 0.5 ppm almost looks clear. At 1 ppm, most people can very readily see the light pink coloration in the volumetric. And then as you go higher, 5 definitely very apparent, 10, 25. And then as you get above 100 ppm, it starts to get darker and darker. You'll hear many of us at Carus refer to dosages for permanganate either in milligrams per liter or parts per million. Just keep in mind, those are interchangeable. They mean the same thing when we're dosing into drinking water. So 1 part per million would be the same as 1 milligram per liter. But we have that distinct coloration. When you first add the permanganate, you're going to have that pink color before it reacts. Now, there are a couple industry standards that you want to be aware of. When you're adding permanganate to drinking water for any application, you really want to ensure that the product meets 2 standards. There's the ANSI AWWA B603 standard, which lists both permanganate as potassium permanganate and liquid permanganate as sodium permanganate, and has standards you want to ensure that the product meets before you apply it to your drinking water. Our product also has the NSF standard 60 drinking water additive testing done on it as well. And so there's a max use level that you'll see on our data sheet and on our SDSs for this product as well. And you want to ensure your product meets that regulation before applying it to your drinking water as well. Both of those are listed on our data sheets and on our product labels that we have those and meet those standards. Now, the reason I bring up all these other applications is typically when we're doing drinking water treatment, you're not treating for one application at a time. So in the case of both groundwater and surface water applications, typically there's multiple things that will react with permanganate when you add it to the drinking water. Some of the most common things that will react, iron and manganese, if you have them in your source water, those are going to react relatively quickly, and you'll have to oxidize those to solids and then coagulate and filter them out. A lot of the things that blue-green algae cause as far as taste and odor issues, those will react with permanganate as well. So there'll be some demand from taste and odor compounds. And then the organics that are in the water that can form disinfection byproducts. So those things that are precursors to THMs and HAAs also can react with permanganate. If you have a lot of natural organic color to the water, so your water has a tea color or a light brown color to it from organics, those are also things that will react with permanganate. And it's all those things that are going to react at the same time as we're trying to do the disinfection byproduct removal as well. Now, on the groundwater side, you might have arsenic or radium in the well, and those are things that will either react or absorb onto the manganese dioxide that's formed. So you want to keep in mind that these are all things that are going to react if you apply to drinking water, and you're going to want to account for them when you do jar testing. So in the case of disinfection byproduct control, what we're looking at is that there's natural organic matter in the water. So typically we talk about what's the starting TOC or total organic carbon level in your water. That TOC is reactive with a variety of things, but the most common is when you add chlorine for disinfectant, it will react with that natural organic matter, the TOC, and it will form THMs and HAAs. Once they form, you're either going to have to absorb them to remove them on carbon or strip them out of solution by aeration, but they're going to stay in solution unless you're doing a removal technique. So one of the ways to prevent the THMs and HAAs from forming is to react with that natural organic matter, that total organic carbon, with permanganate prior to disinfection so that you don't have as much organics to react with the chlorine when you do your disinfection. When we talk about the THMs that they're looking at in drinking water, these are the 4 that they test for. And typically when you get a breakdown, you'll get what's called a total trihalomethane number, so a TTHM number that's reported back to you. A lot of labs will then also break it down between all the different types where it's chloroform, dichlorobromethane, or bromoform. Typically, because we're doing free chlorination in drinking water, chloroform will be the highest level that you have after you've chlorinated the water. That's going to be the largest compound that you see on those lists. In the case of haloacetic acids, referred to as HAAs, typically when you get your report back from a certified lab, you'll see HAA 5 listed. And these are the 5 that they test for. So monochloroacetic acid, dibromoacetic acid. So you can see the list there. Typically there's a spread, but mostly you're going to be toward the chloroacetics. So the mono, the di, and tri, that'll typically be your largest. When you see the bromine compounds, both THMs and HAAs, it typically means you've got bromine content in the water to start with, or you're near a saltwater source, or something else is causing there to be a lot of bromine in the water. And then typically those levels can be higher. It's usually the chloro compounds that are most high when you have THMs and HAAs in a normal drinking water. So there are 2 regulations that plants need to meet for disinfection byproducts. So the original rule was the stage 1 disinfectants and disinfection byproducts rule. The idea for the rule was it was to reduce exposure to disinfectants and the byproducts caused by you disinfecting the water. The EPA website goes into why they set the regulation, but what we have is that the disinfection byproducts have been linked to cancer and to reproductive effects in humans based on the level that a person would consume over their lifetime from drinking water that's been chlorinated or used with a different type of disinfectant like chlorine dioxide or ozone. So the stage 1 rule was put into effect because of that, because they wanted to reduce the exposure to humans from those disinfectants and their disinfectant byproducts. The rule affected any water system that adds a disinfectant during any part of the drinking water treatment process. So if you're disinfecting your water, you're going to be under the stage 1 regulation. The original stage 1 regulation set maximum contaminant levels. So total trihalomethanes was set at 80 parts per billion. Haloacetic acids were set at 60 parts per billion. The monitoring requirements for this regulation was that you're going to take the samples quarterly, and the original stage 1 regulation said it was a system-wide running average. So you average those 4 quarters together as a rolling average, and then determine if you were in compliance with the 80 parts per billion and 60 parts per billion. And the samples were taken throughout the distribution system. So you would typically take one at your plant and then multiples based on your size out in the distribution system and then average those numbers together. Now the stage 1 rule has been on the books and people were to comply with it by January of 2004. So it's been around for a very long time. The stage 2 rule came out based on testing that they had done when the original stage 1 rule had went into effect. And the idea was plants were going to go back out and do an initial distribution system evaluation. And the idea was identify locations where you had high disinfection byproduct concentrations. So target it toward the sites where you had the highest disinfection byproducts. The other thing that it did was it was going to be a locational running annual average, which meant that you no longer averaged the whole system together. So you didn't get to average low sites with high sites. What you ended up having to do was each site had to meet the 80 part per billion and 60 part per billion regulation on their own. And this was called risk targeted monitoring. The idea being that because someone lives far away from the plant and might be exposed to a higher level of disinfection byproducts, they wanted their numbers to be below the 80 and 60, just like somebody that's near the plant would always be below 80 and 60 based on that proximity to the plant and less chance for those disinfection byproducts to form. Now, there was also parts of this rule that talked about significant excursions. So if you did have a short-term peak, they wanted to make you review operational practices and work with your state to identify actions you would take in the future to prevent excursions so that you wouldn't keep having violations of the rule. The rule was finalized in 2006, and systems were supposed to comply with the stage 2 disinfection byproduct rule by October of 2013. In talking to US EPA at the National AWWA show the last several years, the 2 most violated rules typically in drinking water are the disinfection byproduct rule for surface water plants and then the lead and copper rule. So typically when a system has a violation, it's usually one of those 2 things on the drinking water side that causes them to go out of compliance. So that's why this is important to control your disinfectants and the byproducts, because a lot of plants do struggle with this. So there's a couple disinfection byproduct control strategies that you can have. Obviously, because we're talking about chlorinating the natural organic matter in the water, that's your highest level of forming THMs and HAAs is by having the most of your natural organic matter, your TOC, reacting with your highest chlorine dose. So a lot of plants use chlorine as their pre-oxidant at the plant, which means they'll apply their largest dose at the front of the plant, and they're using it to oxidize iron and manganese, oxidize taste and odor compounds. And while they're doing that, it's also reacting with the natural organic matter, that TOC, to form THMs and HAAs. So one of the easiest things to do would be to move the chlorination point from the front of the plant to the back of the plant. So just use your chlorine now for just disinfection and don't use it as your primary oxidant. Now what that does is it delays your disinfection. It also removes your oxidizer from the front of the plant, so you'll have to replace it with something else that can oxidize iron and manganese and taste and odor compounds. And you have multiple options to choose there, but just moving that chlorination point from the raw water at the front of the plant and moving it to just before the filters or just after the filters, depending on your state regulation, usually can give you a very large reduction in disinfection byproducts. Typically as much as 40 to 70% some plants have seen over the years based on just moving that chlorination point. Now, once you remove the chlorine from the front of the plant, you're going to have to do pre-oxidation at the front of the plant. Your options really are permanganate, chlorine dioxide, and ozone. Permanganate typically is always applied at the raw water intake or at the rapid mix at the plant, but will react with that natural organic matter prior to chlorination. And then your coagulation process, you can remove that TOC during that process. What ends up happening is the permanganate reacts with those organics. It reduces the chlorine demand of the water when you do disinfect at the back of the plant. And you typically might see another 5 to 25% reduction in disinfection byproducts by pre-oxidizing with permanganate. The other benefit though is now that you don't have chlorine at the front of the plant, permanganate can react with those taste and odor compounds to remove them. It can react with the iron and manganese in the water and remove them as well. So you get all the benefits of chlorine without the formation of any disinfection byproducts with permanganate. Now, if you do choose one of the other options like chlorine dioxide or ozone, they do form disinfection byproducts. In the case of chlorine dioxide, you will form chloride in the water, and that has a maximum contaminant level daily of 1 milligram per liter that you need to be below. And if you are feeding ozone, there is a bromate limit that's 0.01 milligrams per liter as an MCL on a monthly basis. So if you do choose a different pre-oxidizer at the front of the plant, in chlorine dioxide or ozone, there will be additional disinfection byproducts that you have to test for, and whether it's a daily or a monthly basis for those to make sure that they don't get out in the system. And you'll still have free chlorine at the back of the plant that you'll have to do that testing on a quarterly basis. So if we're going to switch out the front of the plant from free chlorine to permanganate, one of the first things we're going to do is run a permanganate demand jar test. Like you see there in the picture. So we're going to add varying amounts of permanganate to the jar, and then we're going to test to see how much permanganate is consumed over time. So I mentioned earlier, typically where we feed permanganate is going to be at the front of the plant. So ideally, if we've got contact time, we'd love to be at the intake at the raw water source. So if you're pulling from a lake or a river and you can feed there, and there's a benefit as far as the contact time you would have, that would be the best place to feed. Now, if you're right on your river source or lake source and you're only going to gain, a minute, 5 minutes of contact time, then it would be okay to move and feed the permanganate at the rapid mix. A lot of plants will feed permanganate at the rapid mix because it's the easiest setup and they don't gain much detention time. Now, if you're farther away from your source and you can get 15 minutes, 30 minutes, an hour of contact time in the pipeline to the plant from the raw water source to the rapid mix, then that gives you a lot of benefit of feeding far away from the plant and getting all that reaction time going to the plant. Typically, we carry permanganate residual through the rapid mix and into the slow mix, and then depending on where you're feeding, so if you're feeding at the raw water source, typically we'll just carry permanganate residual into the rapid mix as long as we've gotten a good 15 to 30 minutes of contact time. If you're feeding at the rapid mix and we're using that for contact time, we will typically carry it into the slow mix, the flocculators, and we might carry it through all the stages of your flocculators because that usually will get us about 30 to 45 minutes of contact time. And what we need is, because we're reacting with organics, which are slower to react, we do need that contact time. So we really want at least a minimum of 15 minutes with permanganate so that we get some reaction with those organics prior to doing the rest of your process. Now, there's a lot of factors that will affect your permanganate dosage in this jar test. So one of the things you typically will look at when I do this in the field is I'll look at how much iron and manganese is in the raw water that's reactive, so how much soluble iron and manganese, and that'll give me a good baseline for where I'm going to start, because those will react in the first couple minutes. So if I have a demand of about 1 part from iron and manganese, my lowest jar is typically going to be right at 1 part, and then I'll go up from there to like 1.5 to 2.5. The other part is how long do you have in your plant. So we'll sit down and walk through the math, and so if it's from your intake to the plant, how much time is in that pipeline based on a normal pumping day? So how many MGD do you treat and how long does it take to get to the plant? Or if we're in the plant, how much time is in your rapid mix and how much time is in your flocculators? And we'll use that for the detention time for the jar test. A lot of times this is available when the plant's designed, they'll have this in the engineering manual, or we can calculate it from the volume of water in those basins to do it. There is a little bit of a dosage effect. So as I apply more permanganate, some of those reactions will happen quicker. So if I apply a really large permanganate dose, it's going to consume more than a lower dosage would in that same type of water. And then there is a pH effect. Typically, we'd love to be between pH 7 and 8, but permanganate reacts faster as the pH goes up. So if we're in the low 6s, typically we're going to want a pH adjust up into the 7s to get that reaction to go quicker as well. So like I mentioned, application point will be the first thing that we'll discuss prior to a jar test. So are we going to feed at the intake? Are we going to feed at the rapid mix? What's the detention time we have? Ideally, we want about 15 minutes or more. If you've only got a contact time of 1 or 2 minutes, we're typically only going to really be reacting with the iron and manganese, so you're not going to get much benefit from reacting with organics. We do want to keep in mind when you add permanganate that you're not adding all your chemicals at the same time. So powder activated carbon and permanganate do react with each other. It's a slow reaction, but you will consume some of the permanganate on the carbon. So if you can separate the feed points for those chemicals, it's much more efficient use of your carbon and your permanganate. And typically that means feeding permanganate first at the intake and then feeding carbon as a polishing agent at the rapid mix. Coagulants like aluminum sulfate, polyaluminum chloride typically are non-reactive with permanganate, so they don't have a demand. But if you are feeding a copolymer, it's something to check in the jar test to see if that polymer is oxidant resistant. Sometimes polymers will react with permanganate and you won't get good coagulation. So it's definitely something you want to try in the jar. And then obviously you want to try to avoid adding chlorine at the same time as permanganate, because as you form THMs and HAAs, once that THM or HAA forms, it's no longer reactive with permanganate and it will be there. So you really want to do pre-treatment with permanganate to remove those organics, and then add your free chlorine at the back of the plant for your disinfection. And like I mentioned, we'll test for permanganate residual downstream of our application point to maintain control to make sure we're feeding enough permanganate. So the standard jar test that we would do for this is the permanganate value over time method. And what we're looking for is, because there's not a ratio between the TOC that's in the water and how reactive it is with permanganate, we really want to look at specifically your water, adding the permanganate to it, and then looking at how the permanganate reacts over your detention time of say 15 or 30 minutes, and then coming back and measuring how much permanganate residual was consumed. So this will also take into account iron and manganese and taste and odor compounds in this jar test, because you're looking downstream after all those things are reacted. So you could come back and look at iron and manganese to make sure that's all removed during this process. If you were doing a taste and odor jar as well, you could then run your taste and odor jar to make sure that you're not having that taste and odor coming off the sample after you've treated it. And then it also helps determine how much permanganate's reacted with the organics as well. So generally this jar test, we get the raw water, record the temperature. Generally what this means is you're going to grab the water and run the jar test immediately. So what you don't want to do is grab the water the day before, let it sit overnight, and then use that water the next day. As that water sits, it does change a little bit, so that jar test is best if you run it with fresh water. Use a graduated cylinder, separate out multiple samples. Typically, I use 1 liter jars when I do this in the field. And typically you want to maintain that original temperature. So ideally, you run that jar as soon as you get the water, and then you get fresh water if you're going to run a second or a third set of jar tests. You'll dose permanganate to each of those jars. Typically, when I do this, I leave 1 jar without permanganate, and then I'll add permanganate at multiple levels, usually somewhere between 0 and 3 milligrams per liter. And one thing to keep in mind is, because you're going to come back to these jars and measure residual, I usually give myself some time in between those jars so I can come back and measure residual, which will only take 1 or 2 minutes. But you want to have that time so that each jar is close to the time when you're supposed to pull it for residual testing. So one of the things, like I said, will determine the detention time that you have. So after we've calculated that, we'll run the jar test for roughly that amount of time. If you're feeding at the rapid mix and then into your flocculators, you should have in your manual for your plant what the speed for the mixture should be. And so we'll adjust the speeds manually, or if it's a programmable, we'll adjust it to the speeds that it is, so that we get the mixing just like you would get in the plant. And what you can see in those jars is that there's distinctly more permanganate as you go up. And then the last jar is one that was untreated and just the yellowish color of the raw water to begin with. So after we've run this for a set amount of time, we're going to take a sample from each of these jars, and we prefer using the DPD permanganate method that you can get from us. You're going to have to filter the sample. And what we're doing is we're modifying the chlorine powder pillow test. The chlorine powder pillow test turns red, but it doesn't matter whether it's chlorine or it's permanganate or it's ozone or chlorine dioxide. All of those compounds will actually color the powder pillow red, and depending on what compound it was, it'll do it in a slightly different way. One of the reasons we have to filter our sample is when you add permanganate, we form manganese dioxide, which is a solid. Because this is a spectrophotometric method, solids will disperse the light and you'll get a false positive high reading because of those solids. So the first thing we're going to do is take a sample of the water from the jar test and we're going to filter it. And we prefer 0.22 micron filters. You can use 0.45s. Generally, we only use 0.45s though when you've already added the coagulant to the jar, because that'll help bind up the manganese dioxide and make it a larger particle and easier to filter. We use the 0.22s if we're not adding any coagulant. The 0.22s generally will get most of the manganese dioxide out of the sample, and so you'll have a pretty clean sample with just the pink or purple color of permanganate left behind. We zero the spectrophotometer with the filtrate. We then add the DPD powder pillow and we measure the concentration. So it's the exact same way you normally do with chlorine. You're going to add the powder pillow, you're going to mix the sample, and then as it reacts, it's going to turn a distinctive pink to red color based on how much permanganate's there. Now, like I said, the permanganate doesn't react the exact same way as chlorine. So over many, many years at Carus, we've done this, and we know that typically the DPD reading that you get on your spectrophotometer with the chlorine powder pillow, if you're feeding potassium permanganate, it's 0.89 times the DPD reading on your spec will then give you actually how much permanganate is there. So it reacts a little bit less than chlorine does. If you're using sodium permanganate, because of the weight difference between potassium and sodium, the reading goes down a little bit, so it goes down to 0.8 times that reading. So if you get that DPD reading and it was reading 1 as free chlorine, but you were feeding sodium permanganate, you'd really be seeing about 0.8 milligrams per liter as sodium permanganate in the jar. So it's just something, a little extra math that you have to do because we're modifying this method for permanganate. But a lot of plants use this method on a daily basis to track permanganate residual in their plant, and they find it pretty easy to use. So after you've done this set time and came back and measured the residual, so in this case, it was a 15-minute demand in a surface water plant. And in the jars, they dosed 1, 2, 3, 4, and 5 milligrams per liter. Came back and measured the residual, and you'll have how much permanganate was left in the jar. Based on that curve, you can see that there is some flexibility, but roughly what this jar test showed was that if you fed permanganate and came back and measured permanganate residual after 15 minutes, you would typically consume about 0.4 milligrams per liter of permanganate. So what this jar test does is it lets you set up your initial feed rate in your plant, so you're not flying blind by just starting a dose in the plant and then measuring downstream at the rapid mix. So you'll do this jar test. In this case, it says 0.4. So when you would set up at the plant, you would feed 0.4 milligrams per liter at the front of the plant, and then 15 minutes downstream, you'd come and measure residual, and it should just about be gone. And then you can tweak the dosage up and down with the permanganate residual test once you've had this initial established dosage in the jar. So this is a good way just to determine where you're going to start at, and then you can tweak the dosage once you get to the actual plant based on what you're seeing in the plant by applying that permanganate dosage. So we've established the dosage of permanganate that you're going to feed in your plant or where you're going to start at. So what happens when you feed it? So a lot of plants have done this study over the years that we've worked with. And so we're going to go through some case studies. Our first case study here is a plant that was going to look at Carusol versus free chlorine at the front of the plant. And they had two things that they were concerned about. They had high levels of manganese in their water, and they were forming disinfection byproducts. So the plant had groundwater, but it was under surface influence. So the wells were right next to a river nearby. The water came into the plant and it was 5 mgd, and it went through two separate 2.5 mgd active flow trains. So that's a specific type of sand ballasted treatment process. Manganese, depending on what was going on in the river, because of that surface influence, could vary from 0.2 to 0.45 milligrams per liter. And when they were chlorinating, when they did the initial startup for this plant, the THMs were above 80 parts per billion, leaving the filters in the plant going to the clear well. So clearly in violation of the 80 part per billion regulation. So their goal was, they knew they were going to have to replace the free chlorine at the front of the plant, but they wanted to make sure they would get the manganese to below 0.05 milligrams per liter. And their contact time was only about 10 minutes. And they wanted to form no disinfection byproducts, their THMs, in that front part of the process. And they were going to move the chlorine to right before the filters or right after the filters, depending on how the testing went in the plant. So like I mentioned, they were infiltration wells. So the mound of dirt with the fence on top of it is a river that's flowing by, and then the wells were on the property. So you're just really getting riverbed filtration. So as the water quality would shift in the river, that would also shift the water quality coming into the plant. The trial equipment during the plant startup was a tote of liquid permanganate with a metering pump sitting directly on top of it, because it was very easy to add to this plant. Because those wells are right outside the building, there wasn't really any benefit from feeding at the wellhead itself. We would have gotten less than 60 seconds of contact time before the water came into the flash mix. So based on that, they decided they were going to feed the permanganate to the flash mix of the plant. So our application point was to the bottom of the flash mix. Our feed line was threaded through the PVC pipe that was duct taped to hold it below the surface. And you can see that distinctive pink coloration of permanganate as it splits in the flash mix and goes to the two separate 2.5 active flow processes. So in this case, the flash mix permanganate's being added along with their coagulant. And then they add micro sand. They go through a rapid mix area where that sand, the polymer and everything reacts, and the solids stick to the sand. They take away the agitation, the sand drops out carrying the solids with it. They then went from that stage to lamella separators, and then from that step they went to their filters in their plant. But as you can see, we're adding permanganate at the very front of the plant, and then you've got very clean water coming out of the back of the plant at the lamella separators, because all those solids have been removed through the process. Now, when they were feeding free chlorine at the plant, they were having issues with manganese. And so even when they cranked their chlorine dosage up, they were still getting manganese to the back of the plant and through the filters, and they were getting sometimes as much as 0.12 milligrams per liter of manganese into the clear well, and then the water would discolor in the clear well. With the sodium permanganate, they were able to get it down to about 0.025 milligrams per liter of manganese in that limited contact time. And because permanganate doesn't form any disinfection byproducts, the level going into their clear well at the plant was at 0 THMs because they weren't adding the pre-chlorine anymore. So we were able to achieve both manganese removal in the contact time they had in the plant and not form any disinfection byproduct going into the clear well, which was going to be now their first point of contact with free chlorine for disinfection. Our next case study, this was looking at THMs with Carus. It's Elsinore Valley Municipal Water, which is out in California. They're a 37 MGD facility, and their THMs could be as high as 130 to 140. They also were getting some musty, fishy odor complaints, typically 5 to 10 per month coming from their source water. And they chose the treatment of 2 to 3 milligrams per liter as potassium permanganate for their application. So they did a plant trial, and you can see when they had free chlorine on at the front of the plant, at the flash mix, they had THMs about 38. In the settled water, prior to filtration, they were up to 60. The filtered water was at 130, and the clear well was at 140 before the water even went out the door to the distribution system. When they moved the free chlorine back to right before the filters and added permanganate at the front of the plant, you no longer had any THMs formed in the flash mix or in the settled water. And then at the back of the plant in the filtered water, they had about a 35 ppm, and then the clear well was at 40 parts per billion before you went to the system. So you were now at half of the regulation going out to the distribution system. So permanganate was able to be the preoxidizer and form less THMs at the front of the plant. Conclusions for this plant: the THMs were lowered from 140 to 40 parts per billion going into the clear well. So that was about a 70% reduction. And because they'd removed the free chlorine from the front of the plant, they were curious, would the permanganate react with those musty, fishy kind of taste and odor complaints? Well, typically fishy odor complaints are something that oxidize readily with permanganate. And so their taste and odor complaints dropped from 5 to 10 per month to typically about 0 per month. Now, musty odors typically don't always go away. Those are MIB and geosmin, and so sometimes it needs to be a combination treatment for removal. But in this case, with this specific water, their taste and odor complaints went away with permanganate pre-treatment at the front of the plant, where they were still having some when they had been using free chlorine. Another case study. This one's specifically looking at Carus, and it was for control of haloacetic acids. So background, this was a Southern Illinois water treatment plant. It was a surface water. Flow was 4.6 mgd. And in this case, you saw the first two case studies both had issues with THMs. In this case, they were having issues with HAAs with the source water. So one of the things to keep in mind is that TOC, or total organic carbon number, it just depends on what makes up that TOC number, what specific type of organic is there. And then it depends when you chlorinate it. Sometimes you'll get THMs, sometimes you'll get HAAs, sometimes you might have issues with both. So in the case of this source water, HAAs were their concern. So their goal was they wanted to lower their HAAs to less than 30 parts per billion. They wanted to move the chlorine feed point, and they evaluated a couple different treatment options. So they looked at chlorine dioxide, they looked at using powder activated carbon to absorb HAAs, and they looked at potassium permanganate. So they ran multiple tests at this plant, but what they knew is that typically their HAA levels climbed as the water got warmer and they got more organics in the water in the summer months. So you can see their HAAs are actually pretty low in May of the year. They start to climb in June, and they continue to climb during the month of June. So they go from 20 all the way up to just over 45 parts per billion in the span of 2 months. So they started applying permanganate. The initial dose of permanganate they started at was about 0.5. And you can see in July, typically what they would see is their HAAs would still climb. So that initial dosage was able to knock the HAAs from 45 down to just over 30. But in August, because of shifting water quality, that half a part wasn't really able to knock them completely back down to that level of around 30. They started to climb. So they increased their permanganate dose up to about 0.75. And they saw that they did have a downward trend in the HAAs that formed. They increased the permanganate again to 1 milligram per liter as a preoxidant at the front of the plant. And then they saw that the HAAs on the 12th of August continued to drop even lower. Typically, June, July, August, and September for most plants are their highest levels of disinfection byproducts in the plant because of that shifting water quality. So they did see a dosage response. If they added more permanganate at the front of the plant, they would tend to form less HAAs at the back of the plant when they did do chlorination. Now, I did mention that they used multiple ways to get to their treatment goals. And what they found was that all the products they used worked. So potassium permanganate, powder activated carbon, and chlorine dioxide were all able to be used at the front of the plant for treatment, and they were able to get their HAAs under control. Permanganate had the smallest dosage at 1 milligram per liter and the lowest treatment cost at that time. Powder activated carbon took slightly more to absorb the organics, so they had to feed about 2.7, and then chlorine dioxide had about the same dosage as permanganate, but had a slightly higher treatment cost. So they had multiple options to pick, and they had picked potassium permanganate at the time of this test. So things that they looked at this plant was they replaced the chlorine as the preoxidant with permanganate at the front of the plant. They were able to control THMs, and really their big complaint was to keep the HAAs lower. One of the things the operators talked about was, if we're removing the free chlorine from the front of the plant, are we still going to have good iron and manganese removal, and are we still going to have good taste and odor removal? Well, when they made the switch, they noticed that they didn't have more taste and odor complaints, and they still had good iron and manganese control with oxidation. So they were able to meet all their treatment goals with permanganate as the pre-oxidizer and move that chlorine to the back of the plant. Now, one thing they also noticed in this situation was, because we were adding permanganate and we were forming manganese dioxide, which is a solid, they actually noticed that that solid that they formed from the permanganate reaction helped improve settling and helped them aid their coagulation process. So they actually got lower turbidity coming out of their settling basins when the permanganate was fed at the front of the plant. So they noticed this an additional benefit. Our last case study here is a plant that was using Carusol for disinfection byproducts, and they had both THMs and HAA 5 issues. They were a southern US water treatment plant. They could go as high as 40 MGD, but they typically averaged about 27 MGD. And they were surface water from a river source. Their treatment was, they wanted to move pre-chlorination to above the filters. So they were going to move it from the front of the plant to the back of the plant. And they wanted something that was easy to apply at the intake. Now, this plant was directly on the river, so we didn't gain much contact time, but they did have a river pump station, so it was just easy to add the product at that point. Their goal was, they wanted to see, we'll apply a 0.5 milligram per liter of sodium permanganate at the intake and see what the impact is to the water quality. Now, they ran 2 tests at this plant. They ran a winter test when they typically had the lowest THMs and HAAs in the water, and then they also ran this test again in the summer when they had the highest number. And the reason they ran these 2 tests is they wanted to see, the initial idea was, do we need to feed year round? And if we do feed year round, do we see a benefit in the low THM HAA months? And do we see that same benefit in the summer months? Typically, a lot of plants that feed for disinfection byproducts will feed during their taste and odor season and during their warm months when the numbers are the highest, and they'll knock those levels down. So we did the winter test in January to February, and we had pre-chlorination on, and then we compared it to sodium permanganate at 0.5 milligram per liter with the free chlorine on at the back of the plant just before filtration. And when you look at the sample sites at the plant and out in the distribution system, what we saw was, when we moved permanganate to the front of the plant and moved that pre-chlorination back, we saw roughly about a 30% reduction in THMs and about a 50% reduction in HAAs, even in the winter months with the best water quality as far as forming THMs and HAAs. We did see a benefit from feeding the permanganate that time of year. They came back, and during their worst water quality, where they would form the most THMs and HAAs because of the temperature in the water and reactivity, we ran a test in July and August. And you can see with pre-chlorination, the THM levels could be very high in the distribution system, well over 80 parts per billion, where you see a 150 and a 115. And then even the HAAs could climb above the 60 parts per billion level in the system. We have turned on the sodium permanganate and ran the same test, and we still had some sites for THMs that still climbed very high. So we were in the high 90s, low 100s, but the HAAs were all below the 60 parts per billion. When we looked at the math between pre-chlorination versus sodium permanganate, we saw roughly the same reduction in THM. So roughly about 30% reduction in THMs in the summer is the same as what we saw in the winter. HAA removal or reduction was actually slightly better. We went from 50% to 66%. So when we looked at the combined winter-summer test, which would have been only 2 quarters out of the 4 quarters that they would average, if you look at those locational running annual averages, so each site standing on its own, with sodium permanganate on and pre-chlorination at the back of the plant, all the sites would stand on their own for a 2-quarter average of THMs and HAAs being below the 80 parts per billion and 60 parts per billion. With pre-chlorination on, they would have had several sites that had failed. And the reason they had run this test was because they had sites that had failed the locational running annual average based on them having to stand by their own. And you can see some of them are just barely over at 86 and 83 over 80, and the 63 and 65 over the 60 parts per billion. So when they used this data, what they looked at was, do we really need to feed during winter and summer, or can we just feed during the 2 quarters where we have the highest number? And we did see the same benefit, whether it was winter or summer. So the initial setup at this plant was to feed during the summer months. So they were going to feed during that May, June, July, August, September timeframe, and then go back to pre-chlorination in the winter when they had low numbers. So they were only going to feed about 6 months out of the year with sodium permanganate at the front of the plant, and then they'd go back to free chlorine, and that was going to be enough to get them into compliance with the locational running annual average at the site. So they also have the data that if they did need to go lower, they could feed year round and they would still see a benefit in the winter months. But from this data, they were able to make the treatment choices that they had at their treatment plant based on the data they had generated. So in this case, they replaced the chlorine as the pre-oxidant for the summer months. One of the things the operators talked about is they had been feeding free chlorine at this plant for a very, very long time. And they had always had good taste and odor control. They had always had good iron and manganese control coming off the river source. So one of the concerns the operators had was, now that we're feeding permanganate, are we going to be able to maintain that control? And so what was set up during the trial was we're feeding permanganate at the intake on the plant site, and we were measuring permanganate residual going from the flocculators into the sedimentation basin. And so on every shift, they measured permanganate residual going into the sedimentation basins, and the goal was to have about a 0.1 residual at the end of the flocculators going into sedimentation, and then they could make dosage adjustments based on where that residual was. So if it started to climb going into the sedimentation basin, they could back off on the feed rate. If it started to drop off and we lost residual in the flocculators, they could turn the dosage up at that point. So overall, though, we were able to reduce the THMs by 30% and the HAAs by about 65% when they did the full-scale trial after the 2 mini trials. So we've covered many different case studies for THMs and HAAs and the jar testing you would do. Permanganate's been around for over 100 years. A lot of surface water plants use permanganate, and they'll use it for multiple applications. So taste and odor removal, iron and manganese oxidation, and then also for organic removal to help lower disinfection byproducts at the back of the plant. One thing to keep in mind, if you are applying permanganate, we are going to generate manganese dioxide as a solid. So you're going to need clarification and filtration typically. What that means is you're going to have to add the permanganate and then downstream add a coagulant. And then you're going to have filtration to remove those systems, remove those solids. It doesn't matter the size of the plant. It can be a very small plant to a very large plant. The applications are the same. It's just going to be making sure that you feed the right amount of permanganate and monitor it so that you don't overfeed the plant. Like I said, permanganate oxidation chemistry benefits are numerous. Make sure that you can get in compliance with the disinfection byproduct. But also because you're applying permanganate at the front of the plant, you can eliminate those flavors and taste compounds that can form from algae blooms. You can remove color from the water. You can remove iron and manganese. But overall, feeding permanganate at the front of the plant provides overall better water quality at the back of the plant going out the door to your consumer. And with that, there is my contact information. My phone number and my email address if you want to reach out to us. And I'll turn it back to Ashley to see if we have any questions.
All right, thanks, Darin. Thank you everyone for joining today. Like Darin said, if you have any additional questions, feel free to reach out. His phone number and email are listed on the screen now. So thank you again for joining and have a great day.